David Hill, traveling his way up from Oregon, is a professor of civil and environmental engineering at Oregon State University. He's presenting his work on citizen scientists and seasonal snow modeling and how you can get involved. His research is supported by the North Pacific Research Board, the National Science Foundation, NASA, and a handful of other agencies. So let's welcome him up.
Okay, great. How's everyone doing in the back? All right. If there's any small text, I'll be sure to try and call it out for you. I like to try and get to the point right up front. So this is basically my talk, and I'm going to go through each of these three things in a little bit more detail, all right, over the next 15 minutes or so. So if you think about where information on snow comes from, it really comes from one of three places. Either comes from remote sensing measurements, it comes from on-the-ground measurements, or it comes from computer modeling. All right, and I'm involved in some ways in all three of these. To just give you a couple of examples, when it comes to snow modeling, snow models are run for different regions at different resolutions, and all sorts of different configurations. SNODAS is one example that has complete coverage over the continental United States, and it's run typically about a 1 or 2 kilometer resolution. In terms of remote measurements, there's several things that one can talk about. You could talk about the GRACE satellites, which are operated by NASA. You could talk about the Airborne Snow Observatory, which is operated by JPL. And what you're looking at here in the lower left, this is typically done every month. This is a map of snow water equivalent, which is inferred from LiDAR depth measurements of the snowpack. In situ measurements are actual measurements made on the ground, and these can be made in a wide variety of ways. You can either just use a simple tape measure, if you like. You can use an avalanche probe, if you like. You can also use snow coring devices, which allow you to measure both the depth of the snowpack as well as, once you weigh it, information on the water equivalent of the snowpack. This is a map of all of the snow telemetry stations in the United States. There are none on the East Coast. There are some operated by the SCAN network, but there's only a few on the East Coast. In the western United States and up in Alaska, all told, we have about 800 to 900 SNOTEL stations. Canada has an equivalent network of snow pillow measurements as well.
There aren't any in the Sierra Nevadas?
Yep. Yeah, right. They're there. Right in here. This big cluster right there is the Sierra Nevada, yes. So these are all excellent sources of information, and we use them all the time. Snow scientists do. They are typically, when it comes to SNOTEL sites, they're fixed locations, so it gives you high temporal resolution, hourly or daily measurements of snow information at those fixed locations. If you think about something like the ASO, you get very, very good spatial coverage, so not just a fixed point like a SNOTEL station, but this is only done for a few regions, okay, sort of near the Tuolumne area here in this case, and they tend to only be done, let's say, on a monthly time step because they're very, very expensive campaigns. So we were sitting around thinking about other ways of collecting snow information, and that's what led to this Community Snow Observations project. And a group of us got together and started just thinking about the fact that backcountry users are really interesting data collection opportunities for a number of reasons. Backcountry users tend to travel significant distances over large elevational transects, so they go far, they go high, they also go into areas of complex terrain. All right, and things like snow telemetry stations tend to be located in areas of not so complex terrain because they require typically vehicular access to install them and to maintain the instrumentation. So backcountry users are a really, really good untapped source of information. So essentially our project goal is to try and incorporate citizen scientist measurements of snow depth, okay, of snow information, and incorporate that into the modeling chain that we use to basically build better models and allow us to do a much better job of high spatial resolution, high temporal resolution models of the snowpack. Now, with a little bit of experience doing this, there's several things that we have to keep in mind. First of all, we have to keep the bar as low as possible to participation if we want to get people to participate. All right, and one of the first things we thought about is it really shouldn't require anything special. Okay, we don't want people to carry around federal samplers in their backpack. They're big, they're heavy, they're clunky. So we really don't want to involve any new equipment. And we all carry safety gear, right? And you know, the photograph that you have of me in your program there is a conveniently cropped picture of this, which is from last year on Middle Sister in Oregon. And this is a picture of the Mount Cook Visitor Center in New Zealand, where we spent some time last year. Great visitor center. They have an amazing museum where you'll find hobnailed boots, wool, hemp ropes, and the F1 Focus beacon. So I promptly came home after that trip and bought a modern version. So it is important to carry your safety kit, maintain it, change the batteries, and buy a new one more than every 2 or 3 decades. So thank you for cropping that out of the picture. The second thing is that this needs to be easy. It needs to be fast. We can't ask people to do a lot because, you know, your weekend days are precious. You got objectives. You want to go ski and so on and so forth. And so we designed this to be very, very quick. It only takes a little bit of time. And we hope that more and more people will participate. And then finally, it needs to be easy in terms of, you know, you make a measurement and you're done, okay? Your responsibility ends there. We take over. Everything becomes automatic. And so we have this very, very automated process of getting data and building it right into our models. So if you're interested, what you really need to do, first thing is everyone's on board with this. I have to go outside, okay? I don't have to do any arm twisting to get people to do that, all right? It's very, very simple and straightforward. The second thing that you have to do is you do have to take a probe, okay, or some other measurement device. And then the third thing is you have to take your phone, all right? And I know phones are getting better in terms of batteries and so forth, but put it inside your jacket, keep it warm, try and keep the battery life going, okay? So in terms of what one actually does, it's really straightforward. All we are looking for people to do is take a depth measurement, all right? Stick that probe in. It's got to go all the way to the ground, okay? So I sometimes hear from people, what do I do if I'm up in British Columbia and the snowpack's 5 meters deep? That is a place where this program falls short, okay? But typical probes are about 3 meters, all right? So stick it in the ground a few times, cover a couple of different areas, try and get an average depth measurement. Next thing you have to do is enter this into your phone. Now we've partnered with Mountain Hub, which has been recently acquired by Mammut. And some people have asked, well, why do you use that app? Why don't you use a different one? And we're trying to be as inclusive as possible. Mountain Hub has changed their app to meet our needs in the sense that they've included a snow depth field. So it's super simple. You just walk through, submit an observation, here's the snow depth, hit send, and it comes right to us. All right? We are also collaborating with other groups to try and get access to data that might come from their apps as well. Okay, one of those is Snowpilot, because initially when talking to a lot of people that work in the avalanche forecasting area, they're like, we don't want to use a new program, we already have something, and we've heard from a lot of people that Snowpilot is a preferred way of submitting information about snow profiles, and that's absolutely fantastic. So we work with Snowpilot, all that data comes to us as well, all right? And we'll continue to expand those collaborations in the future. Okay, so where does the data go? Who can use it? Anybody can use it. You can view the data, okay, through the Mountain Hub app. You can view the data through our website. All right, so if you go here, there's actually a data tab, and you can sort of, and it's global, you can sort of pan and zoom in and out all over the globe and see where these measurements have come from. And then finally, if you like to geek out on data, you can use our API, and you can actually get all of the data, you can download it, and you can play with it yourself. All right, so there's options for the casual user or a more involved scientific user as well. All right, so that's great. That's the whole, can we collect snow data? Yes, please do, participate. But then next question is like, well, you've told me how do I do it. Now, why would I want to do it? What do you guys do with it? What is this data good for? So this first step is basically we take CSO snow depth measurements and we turn those depth measurements into snow water equivalent, okay? Now, how dense you have to know how dense the snow is to do that, and it's kind of a complicated story because these are some great profiles from a really old paper in Journal of Glaciology that basically show that down low, at low elevations, okay, the snow is not very dense, it's fairly light. You go higher, it gets denser because it's deeper and you have densification effects and so forth. But you go higher still and it gets light again, okay? So that's a little bit of a subtle effect. So what we've done recently is this is basically a map of all of the snow telemetry data points ever, okay, from the USA network. There's about 2.5 million points on that plot. which relates snow depth on one axis to snow water equivalent on the other axis. And clearly there's some relationship there. And so we do a lot of regression analysis to try and sort out what this relationship is, and it allows us to build a model that will give us, on the vertical axis over there, our model predictions of the snow water equivalent. And we're comparing that against what the snow tells stations in terms of the observations of snow water equivalent. And for a statistical model, that's actually a really nice job. Okay, and this gives us an idea here on the horizontal axis. This is basically a measure of the size of the errors. And they're actually fairly respectable. So we feel really good about being able to take citizen scientist snow depth measurements, turn those into snow water equivalent estimates. So the next thing, and this is sort of step 2 in this modeling chain, is now we run a snow model. And there's all kinds of snow models that you can run. They take weather information, they take elevation information, land cover information. You do a whole bunch of things, and what do you get out of that? Well, you get predictions of things like snow water equivalent, snow depth, melt rate, all those kinds of interesting variables. And so this is kind of just an example. We actually end up running a suite of models by Glenn Liston and his collaborators called Snow Model. We force it with a certain weather product, fair enough. We tend to run these models at 30 to 50 meter spatial resolution. And these models have the ability to assimilate data. So in other words, as you're running the model for a water year, if we get a citizen science measurement, we bring it into the modeling chain and it gives a correction. And that helps the model always be sort of chasing reality and chasing on-the-ground observations. So that brings us to step 3, right? So up here we have the snow water equivalent estimates in the upper right. Those come from our citizen scientists. We now have other model estimates of snow water equivalent, and we just take the difference. And we use that difference to constantly be fixing the models, all right? And it works really, really nicely. To try and show you that it works, I'm going to give you one case study here. This is near Thompson Pass, which is just east of Valdez, Alaska. Wonderful place to ski, really big outdoor ski community. All of those red symbols that you see there are citizen science measurements of snow depth at a given time. This was for the 2017-2018 water year. Okay, so what I'm showing you here is a plot of the modeled snow water equivalent on the vertical axis against the measured snow water equivalent at the snow telemetry station near Thompson Pass. And this is the best case model run that we have. We've calibrated the heck out of it. We've turned all the tuning parameters and so on and so forth. And it's terrible, okay? You can see that the points don't come anywhere near the diagonal line, which would indicate perfect model agreement. The model snow water equivalent is way too high. Now the reason for that is really has to do with weather data and the challenges that we have finding the best weather data. So this is basically showing you the black lines are the measurements of cumulative precipitation and temperature at the snow telemetry station. The blue lines are essentially what we're getting from the weather reanalysis data that we're using to drive this model. And basically you can see the model is way too wet. Okay, the blue line is far above the black line in the lower panel. And also the model is too warm. All right, so basically, but in the winter months where the model is too warm, it's still below freezing. So the problem here has to do with the weather. This reanalysis product is dropping way too much precipitation on the area, and it's giving us a snowpack which is way too deep, okay, and way too wet. This is what we get when we rerun everything with our citizen scientist observations, okay? And these points are now almost spot on that one-to-one line. And the errors have been cut by about 95%. So just having people in a very opportunistic way, we're not telling them where to go, we're not telling them when to measure, they're just doing their thing as they're recreating. And it totally fixes everything. So it's really, really powerful, the impact that casual users can have, okay, on the type of scientific modeling that we want to do. Okay, the lesson is citizen scientists are amazing, so we appreciate everyone that's participating in this program. It started in Alaska, it's coming down into the sort of the lower 48, all right, and we're seeing it grow a lot last year, and we're really, really hoping that people will get interested in this project. It doesn't take much time. So where we're going now, basically, we're upscaling the project in terms of we started off just modeling Thompson Pass. We're now starting to bring in model domains, okay, and other locations. We're doing some interesting science in terms of trying to figure out, like, okay, that correction we saw was fantastic, but did we need that many measurements? Like, could we do with a few less? Or like, could we, you know, if you wanted to do your own measurements, could you go out just once a week or twice a week? Or do you have to cover both low areas and high areas? So what's the sampling strategy? Or what's the citizen scientist measurement strategy that might do the best job? And finally, of course, this is an ongoing thing, right, in terms of just trying to recruit and retain participants. Okay, so I think that about sums it up. We've had a great kickoff to this project. It's great having people get involved. They go out and make measurements, and they come and talk to us, and they're like, hey, just by actually measuring the snow, I feel like I'm learning stuff. I'm seeing where it's deep and where it's shallow and how it changes from month to month. All right, so we're thankful for data to come in, and we're also starting to push products out and sort of information out to the public, and we hope that it's sort of an ongoing collaboration. So thank you very much.